Shall we start?
Yes, sir.
Yeah. Yeah, welcome to the APRG seminar this week, and we are pleased to have Jan Frahm from Aarhus University, and he'll be talking about resonances for pseudo-Riemannian hyperbolic spaces. You can start now.
Thank you very much, and thanks for the invitation. So when I learned about this seminar, I was invited. I was thinking about a topic, and I saw that many of you are working on Riemannian symmetric spaces and analysis on Riemannian symmetric spaces. So I picked this project that I have with Xenia Spigliotti, who's now at the University of Athens, which is not directly about Riemannian symmetric spaces, but about something slightly different, pseudo-Riemannian, certain pseudo-Riemannian symmetric spaces. But they have several things in common with Riemannian symmetric spaces, and maybe you can understand this as an advertisement for trying out some pseudo-Riemannian things in this setting. And the analysis we were doing was about resonances. So here's a brief outline of my talk. I first want to talk about resonances and explain what resonances are, then talk about these pseudo-Riemannian hyperbolic spaces, about the harmonic analysis on these spaces, and towards the end, put these things together, resonances and hyperbolic spaces. So let me start talking about resonances. And let's start with the Riemannian setting, which you're maybe more familiar with. So let's start with a complete Riemannian manifold, and let delta denote the Laplace-Beltrami operator. If you usually have the negative one, put a minus in front of it, so this is the positive Laplace-Beltrami operator. Then this operator acts in L2 of x with respect to the Riemannian measure as an unbounded self-adjoint operator, as a spectrum, spectral decomposition. And you can consider the resolvent. So Laplacian minus z times the identity is invertible whenever z is not in the spectrum of this operator, and is a bounded operator in L2. And as a function of z, of this complex variable z that's varying in the complex plane, take away the spectrum of the Laplacian, this operator valued family is holomorphic in the parameter z, as long as you stay away from the spectrum. And now here comes the problem. Imagine the spectrum is continuous, maybe the full positive half line. Is it possible to extend this as a holomorphic or meromorphic function across the spectrum? And I'll have some pictures and some examples in a moment. So the first problem is trying to extend this resolvent in a meromorphic way across the spectrum. In the second step, you could wonder if I can extend this resolvent. Does it have poles? Does its extension have poles? And those poles are usually called resonances or quantum resonances. And if you have a pole, you can ask, what is the residue operator? So your function capital R has values in bounded operators on L2. So taking the pole would be an operator on L2, or maybe an operator on some function spaces. What is this residue? What is this operator? What is the image maybe? The general question about resonances is related to solving certain differential equations, certain PDEs. For example, the Schrödinger equation and its single group are related to the location of the resonances, the long-term behavior of these solutions. So that's maybe mathematical physics motivation for studying resonances. And there's lots of people having studied resonances before in various different settings. Many of these people, like Borthwick, Mu, Mazzeo, Melrose, Sjöstrand, they have considered resonances on rather general Riemannian manifolds, maybe with a certain behavior at infinity. Others like Hilgert and Pasquale and Roby have studied resonances on symmetric spaces, Riemannian symmetric spaces, and I'll come to that a little bit later. And others like Tobias Weich and Guillermo, Martin Olbrich, have tried to study resonances on locally symmetric spaces. So Riemannian symmetric spaces modulo discrete torsion-free subgroup. So there's lots of work on the Riemannian setting, and let me maybe give you a few examples to understand the meaning or the the importance of resonances. Let's look at a compact Riemannian manifold. In some sense, this will be an extreme example that's not going to be so interesting, but let's just try to get a feeling for resonances. So if you have a compact Riemannian manifold, the spectrum is discrete, consists of eigenvalues, they have finite multiplicities, and you can diagonalize the action of the Laplacian. So you can find an orthogonal basis of your L2 space consisting of eigenfunctions with with increasing eigenvalues. If you take a fixed eigenspace of eigenvalue z0, then you know how the resolvent acts, because the Laplacian acts by z0. So the resolvent acts on this finite dimensional eigenspace by z0 minus z inverse. And you know exactly where this function has a pole at z equal to z0. So you find that the resolvent as an operator valued function is meromorphic, and it is already meromorphic as a function in one complex variable, and the poles are exactly the eigenvalues. And for each eigenvalue, on all the eigenspaces different to this eigenvalue, this function z0 minus z inverse will be holomorphic, because if z is not equal to z0, then this function is nicely holomorphic. On the eigenspace with eigenvalue z0, this function has a simple pole, and its residue is 1 or minus 1, depending on the sign. So as soon as you pass to the residue, all the eigenspaces with different eigenvalue will be acted upon by 0, and on the eigenspace that you're considering, you're acting by 1 or minus 1. So what you get as residue operator is just the orthogonal projection, maybe up to a sign, onto this eigenspace. So to get a feeling for resonances in this compact setting, resonances are just the eigenvalues, and residue operators are just orthogonal projections onto eigenspaces. So these questions that I had on the previous slide, they tell you everything about the spectral decomposition of your operator. And in some sense, you can view resonances as a way of associating to a possibly non-compact Riemannian manifold also a discrete set of spectral invariants, like the eigenvalues in the compact setting. But we know that if the manifold is non-compact, the spectrum is usually not discrete anymore, but you still want to have a discrete set of invariants, and resonances would give you something like this. Maybe a set to distinguish different manifolds, or a set to read off certain information about PDEs. Now let's assume that we're not in the compact setting anymore. Let's assume we have a continuous spectrum, say a half line from z0 to infinity in the spectrum. Then the situation is like this. This green axis is part of the spectrum. Let's maybe assume this is the whole spectrum. And we have the resolvent as a function on the complex plane, which is slit by this half axis. And we would like to extend the resolvent across this half axis. But the problem is often that if you approach the axis from the upper or the lower side of the complex plane, then you get different limits. So you cannot extend it to a holomorphic function on C, or a meromorphic function on C, but you rather have to extend it to a covering, where you slit the complex plane at this axis and then go to a covering, like winding up like a helix. And in many cases, a double covering suffices, and this will also be the case in today's talk. So if we slit the complex plane here and use the covering map, which maps complex number zeta to zeta squared, and then also move the z0 to the origin, then we get this covering map that maps zeta to z, which is z0 plus zeta squared. And in this way, all the complex plane removed, the way we removed this green line, corresponds to the upper half plane here, or the upper half plane gets mapped to the complex plane slit by this axis. The spectrum that sits on this green line here will correspond to this blue line, which is exactly the real line. And then the second sheet of the covering will correspond to the lower half plane. So you can reformulate the question of extending a function or an operator valued function like the resolvent on this slit complex plane to a double cover of this slit complex plane. This is equivalent to saying that as a function of zeta, the resolvent will extend from the upper half plane across the real line to the full complex plane. So if we, in the formula for the resolvent, write z0 plus zeta squared instead of z. Then we have this as a function of zeta. And it's initially defined for zeta in the upper half plane, and we would like to extend it across the real axis. This is equivalent to extending the classical resolvent R of z across this the spectrum to a double couple. So the goal is to extend this slightly modified resolvent as a function of zeta from the upper half plane across the real line to the whole complex plane. And let's take maybe the simplest example. Or maybe the simplest example was a complex manifold, but let's take the simplest example of a non-compact manifold. Let's just take the real line with a typical Laplacian minus ddx squared. Here we know the spectrum is the full positive half line, so it's purely continuous. And z0 on the previous slide is just the origin. So we consider the resolvent as a function of zeta squared here, which is in the positive, in the upper half plane. In the upper half plane, it's a holomorphic function we'd like to extend across the real line. So we use the spectral decomposition of the Laplacian, which is given by the Fourier transform. And in the L2 sense, I can write function f as an integral over the Fourier modes e to the I x times xi, and the Fourier transform is giving me the intensity of these frequencies. And written in this way, I can simply apply the resolvent because I know how the Laplacian acts on these functions in x. It acts by the eigenvalue I minus xi squared. So I get that delta is acting on this function by xi squared. And if I subtract zeta squared, I get xi squared minus zeta squared. So as a function of zeta in the upper half plane, this is well defined because if zeta is in the upper half plane, zeta squared is away from the real axis, so we never have a pole here. Now the question is how to extend this meromorphically in zeta across the real line. So I want to cross the real line. And for that, natural thing to do is to do a contour shift. Shift the contour from the real axis to some copy of the real axis, which is moved further down in the complex plane. So let's shift the contour from the real axis to the real axis minus I times c for a suitably large c. But if we want to shift the contour and not change the value of the integral, we need that everything is holomorphic. And the denominator is certainly holomorphic. The numerator, at least these functions are certainly holomorphic, but f hat of xi is not. If you just start with an L2 function, this is just an L2 function of xi. So if we want to do this extension, we need the Fourier transform is holomorphic. So natural, maybe modification of the question of extending the resolvent is to view it as a function not on an L2, but on the space CC infinity, where we have a Paley-Wiener theorem and know that the Fourier transform is a holomorphic function. And maybe with values in a large enough space so things will not be a problem. Let's say distributions on R. And sorry, I want to have n equal to 1 here, so n is just 1. Good, then we have the Paley-Wiener theorem. If we take a smooth compactly supported function, f hat is holomorphic, so I can make a contour shift. And this function is now holomorphic in xi, not meromorphic in xi. I can shift the contour to r minus ic. And if c is large enough, I pick up exactly one residue. And that's, remember, zeta to start with is in the upper half plane. And I move into the lower half plane. So zeta could be equal to minus xi, or xi could be minus zeta. So this is the factor which would produce a pole, pick up the corresponding residue, otherwise we get the same integral here. And this is now holomorphic. If C is large enough, it's holomorphic, even in a region where zeta is moving across the real axis into the lower half plane. And we can always make C larger. So this is holomorphic. This is part of our holomorphic extension. How about the residue? Well, we can compute it directly. We know how to take the residue. This is the only part that's giving a pole. So it's this expression.
Actually, we couldn't able to hear you for a second.
Okay, where should I start? with the residue?
Yeah, so
or?
the thing is, you shifted the contour and then.
Okay, yeah, we shift the contour from the real axis to a copy of the real axis, which is moved into the lower half plane. And if we move far enough, with C large enough, then because we fix zeta in the upper half plane, we pick up exactly one residue, and that's due to this psi plus zeta in the denominator. That can get 0 if psi is equal to minus zeta. So we pick up exactly one residue, and we can compute the residue. Everything else is holomorphic, so it's the residue in this. This is kind of giving the -1 term in the Laurent expansion. So the residue will be removing this part and just plugging in psi equal to minus zeta everywhere else. So this is the residue. And this again is holomorphic in, sorry, not holomorphic, but meromorphic in zeta. So we said the first part was holomorphic in zeta. And the residue is now also meromorphic in zeta, or the numerator is actually holomorphic in zeta. And in the denominator, we see that we have a simple pole at zeta equal to 0. So viewed as an operator, the resolvent will have a simple, the resolvent can be extended meromorphically in zeta. And the meromorphic extension to the whole complex plane has a simple pole at zeta equal to 0. And viewed as an operator from a function, say a test function to a distribution, it's given by mapping this test function to this expression, remove the zeta. It's where the pole is at zeta equal to 0, at zeta equal to 0. So it's just the minuses cancel and 2 pi I divided by 2. And then f hat at 0, e to the I 0. So I just get this expression for the residue. And this has to be viewed as an operator. So it maps a test function f to the distribution that's not depending on x anymore. So it's a constant function. So in the one-dimensional Euclidean case, the resolvent has a meromorphic extension, and it has a simple pole at 0, and the residue operator is given by the map that maps every test function to the constant function with value pi I Fourier transform with value at 0. You can also try to do this computation in other dimensions. There things become a little more complicated. You use polar coordinates. Sometimes you can have logarithmic singularities. Sometimes you have no residues at all, depending on whether n is even or odd. But this gives you a flavor of how the argument runs. If you want to do a meromorphic continuation of the resolvent, you try to get a spectral decomposition, move the contour, pick up residues, and analyze everything. And exactly the same thing was done for Riemannian symmetric spaces of rank 1. So let G mod K be a Riemannian symmetric space of rank 1. We also know we have purely continuous spectrum here. And here the spectrum starts with rho squared. That's the bottom of the spectrum, where rho is the usual half sum of the positive roots. And again, we consider this modified resolvent, where we kind of incorporate this double covering of the slit complex plane, slit by this half axis. We need a spectral expansion of the Laplace operator. That's given by the Fourier inversion formula on the symmetric space. And since it's of rank 1, it's just integral over R again. And now the functions e to the I x times psi are replaced by the spherical functions. So this is the nowhere vanishing family of spherical functions. Depends holomorphically on the spectral parameter I nu. And which makes things a little more complicated in this setting is that we have the C function, Harris-Chandler C function. But it's also very explicit in terms of the Ginikin-Karpelevich formula. You can write it as a quotient of lots of gamma functions. And if the space is of rank 1, it's even more explicit. So in this setting, Miatello-Will and Hilgert-Pasquale carried out this analysis. They showed that basically using the same strategy as on the previous slide, this resolvent has a meromorphic extension to all complex parameters. And while the resolvent was holomorphic on the upper half plane, its extension is not holomorphic anymore. It has poles So there are resonances located in the lower half plane, and this would correspond to the second sheet of the covering. And they're located exactly at the points minus I times either rho plus k or rho plus 2k, where k is a natural number. And they also, and this either whether it's k or 2k depends on the symmetric space and some multiplicities, whether they're even or odd. That's not so important. So more important is that they're also able to determine the residue operators, and think of these as the kind of generalizations of projections onto eigenspaces. They all have finite rank. This was also the case for the Euclidean Fourier transform. There the rank was 1. You just get constant functions in the image. And here you get possibly higher dimensional images of these residue operators. And since everything here is done in a G equivariant way, where G is the isometry group of your Riemannian symmetric space, these images will be representations of G, finite dimensional representations of G, and they determine the highest weights. So in some sense, they determine in this way what the residue operators are doing. And this is where our project starts. We were using these pseudo-Riemannian symmetric spaces that I will allude to in a moment, in a different context. And the harmonic analysis is not so different from the Riemannian case. So when we got aware of this work, we thought, why not try resonance?
This result, okay, I have some questions.
Sure.
This result is for rank 1. But what about higher rank symmetric spaces and other?
Yeah, that's a good question. I think Hilgert-Pasquale and Thomas Prischbinder tried rank 2 symmetric spaces, and I think they were able to treat almost all of them, but more or less case by case. And the problem is that maybe it's not the right thing to do, because in higher rank you have not only the Laplacian, but you have a full algebra of invariant differential operators. So maybe one should do a different thing. Maybe one should consider resonances as something coming from the whole algebra of invariant differential operators. Because in their analysis, so I think they were able to work this out for rank 2 spaces, for almost all rank 2 spaces. But the results seem to be not very uniform. So maybe it's not the natural thing to do. Maybe one should think in a different way. But for rank 1, it's carried out and it's already extremely technical. So I don't think it's feasible to do this in higher rank, or higher than 2. Yeah, we were wondering about the pseudo-Riemannian case, because there has not been much study of what resonances are in the pseudo-Riemannian setting. And there are some pseudo-Riemannian symmetric spaces of rank 1 that provide like a nice playground for this problem, just to see what happens in some very symmetric cases, for some very symmetric manifolds. So let me explain what these pseudo-Riemannian hyperbolic spaces are. And if you know Riemannian symmetric spaces of rank 1 very well, then you might recognize several things. So we start with F, either the real complex or the quaternion field. In some of the formulas, we need D to be the dimension of this over R, so either 1, 2, or 4. And we need 2 integer parameters, P and Q. And then there are 2 different definitions of these hyperbolic spaces. Let's first start with a geometric one. We look at the quadratic form. If you think about the reals, it's just the standard quadratic form of signature P, Q, or maybe Q, P. Certainly induces a pseudo-Riemannian metric on the space. But that's not the space we want to consider. We want to consider the hyperboloid. So the level set of where the quadratic form is equal to -1. This is a closed submanifold, and the quadratic form will induce a Riemannian metric on this closed submanifold. And we also want to mod out by the U1 action, where U1 is either O1, so plus minus 1, or the circle group in the complex case, or SP1 in the quaternionic case. And that's because the quadratic form here is invariant under the action of this U1 group coordinate-wise in every coordinate. So in this way, we get get a quotient of a closed submanifold by this compact group. And the quadratic form will also induce a pseudo-Riemannian metric on this quotient, and this is the signature. So that's the geometric definition. If you like groups, and if you think in terms of Riemannian symmetric spaces, you might want to determine the isometry group of this of these spaces, and that's an indefinite unitary group. So this could either be
U1, F will act on this X. So what is the action here?
The action is from the right, but it's you're acting with a number in R, C, or H on each component in this with the same just by dilation.
Component-wise multiplication.
Exactly, but from the right, that makes a difference in the last case. Yes.
Okay.
This doesn't play a big difference. So in the real or the complex case, you could also, at least in the real case, you could also omit it. It's just modulo plus minus 1. That's not so important. Think of this as maybe a closed submanifold. Yeah.
Yes.
So the isometry group is one of these indefinite groups, either indefinite orthogonal, indefinite unitary, or indefinite symplectic group. And you know the rank 1 symmetric spaces will correspond to the ones where you have P or Q, either P or Q equal to 1. That's when the groups have rank 1. But these groups leave the quadratic form invariant, so they act on the level set. And since the action of these groups will be from the left, we'll commute with the action of this U1F from the right. So the group G will also act on the quotient. And the stabilizer of, say, the first standard basis vector in this quotient will be a group of this form. And this U1 factor is something you only get if you have modded out by U1F before. That's why we do this, because now this becomes a symmetric subgroup which is given by the fixed points of an involution, just like the one you want to have when you have a Riemannian symmetric space. The difference is that in the Riemannian symmetric space setting, this will always be a compact, maximal compact subgroup. Here it's not necessarily compact. It's compact if and only if this group is definite. So either if P minus 1 is 0 or if Q is 0. So it's a certain family of pseudo-Riemannian manifolds with the action of a group, which we understand quite well. Let's look at some examples to get a feeling for this. So these are the spaces. First of all, they're actually compact if Q is equal to 0. Because if Q is equal to 0, this group is already compact. It's just an orthogonal, unitary, or symplectic group, compact one. And you mod out by a symmetric subgroup, U1 times UP minus 1, for example. So you get a classical compact symmetric space. We don't want to do compact spaces. For compact spaces, resonances are not so interesting. They're just eigenvalues. So let's assume Q is at least 1. Then it will be non-compact. If Q is at least 1, this space will be Riemannian if and only if P is equal to 1. Because if P is equal to 1, then this subgroup will be compact. So we're modding out by a compact group, actually a maximal compact subgroup, and you get your usual family of classical Riemannian symmetric spaces of rank 1, orthogonal, unitary, or symplectic. We also don't want these because they were treated before by Hilgert and Pasquale. So we assume P is at least 2. So we really get something pseudo-Riemannian, non-compact, pseudo-Riemannian. And these are actually semi-simple symmetric spaces, not Riemannian, but pseudo-Riemannian, and they are of rank 1. So in some sense, you should view them as the counterpart of rank 1 Riemannian symmetric spaces. You get some spaces which are relevant in physics. In the real setting, if Q is equal to 1, you get basically de Sitter space. P is equal to 2, you get anti-de Sitter space. So this is something that's relevant in mathematical physics. And you also get one more exceptional case, just as in the Riemannian symmetric case, related to F4. You can treat it along the same lines. It doesn't make a difference whether you include it or not, but it's a little more tedious to define because of the non-associativity of the octonions. So maybe keep it in mind, but it's not so relevant. Let's think of this family of classical spaces. Good. We would like to do harmonic analysis on these spaces because we need the spectral decomposition of the Laplace-Beltrami operator to say something about resonances. So what is the Laplace-Beltrami operator on these spaces? This is just the setting from before. We have a pseudo-Riemannian manifold, and as soon as we have a pseudo-Riemannian manifold, we have the Laplace-Beltrami operator, and we have a Riemannian measure. And since the metric here was invariant under the isometry group, under this group G, this indefinite orthogonal unitary or symplectic group, all these data will also be invariant. The Laplace-Beltrami operator will be a G-invariant operator, and the Riemannian measure will be G-invariant. The big difference between this case and the Riemannian case is that the Laplace-Beltrami operator is not elliptic anymore, also not subelliptic or anything, not hypoelliptic. So eigenfunctions could also be eigendistributions. They're not necessarily functions or not necessarily smooth. So that's something you have to be a little careful about here. But still, the Laplace-Beltrami operator acts in the L2 space, and you can show in this setting that it's also acting in a self-adjoint way. So you would have a nice spectral decomposition, and here's the spectrum. The spectrum consists of, and this is very much like in the Riemannian case, a positive half-line starting in rho squared, where rho is something related to positive roots. But in addition, you get a discrete set of eigenvalues. And while the spectrum of the positive Laplacian on a Riemannian manifold was always positive, these eigenvalues form a sequence that tends to minus infinity. So in addition to this half-line, you get a part which consists of eigenvalues. Still, you can consider the resolvent. The spectrum contains this half-line, so we want to again view this as something on the double cover. But now we have these eigenvalues. How do they play into the picture? So now the spectrum, the green half-line is still the one that we had before. This should be rho squared. I'm sorry, that's a mistake. But in addition to this half-line, we have a set of discrete points. Let's call them zk. If we do take the same covering map, the same 2-to-1 covering, then these points will lie in the upper half plane on the imaginary axis. So they are exactly the ones that get mapped to these points zk. And before we had the resolvent as a function on the upper half plane, a holomorphic function on the upper half plane. Now it's not holomorphic, but it's at least meromorphic on the upper half plane. These eigenvalues do not cause a big problem for meromorphicity, as we saw in the case of compact manifolds. They will just produce poles of first order, and the residue operators will be projections onto the eigenspaces. So we still have a meromorphic function on the upper half plane, take away these discrete set of eigenvalues. You can still ask the question, can this meromorphic function, this resolvent, be extended across the real line, which corresponds to the continuous part of the spectrum, to the full complex plane? And that's what we'd like to do. And for the Fourier transform in the Euclidean case, and for the Riemannian symmetric spaces, we needed the spectral decomposition of the Laplacian. So let me give you the spectral decomposition here. This is a result which is for real hyperbolic spaces due to Strichertz and Grossman from the 70s. And Jacques Farot found a way of treating all these hyperbolic spaces for the reals, complex quaternions and octonions in a uniform way. So I take the notation from Farot's paper. And but to start with, it looks, at least the continuous part looks very much like the one for Riemannian symmetric spaces. You have you have an integral over the spectral parameter nu. You have a C function, and you have convolution with now not spherical functions, but because the Laplacian here is not elliptic, these will be spherical distributions. But you can define them in a similar way. They will be distributions on X, or distributions on G if you want, which are invariant both from the right and from the left under your subgroup H, under the stabilizer group. And at the same time, they're supposed to satisfy a certain differential equation. The Laplacian applied to them they should be eigenfunctions of the Laplacian. And well, in the Riemannian case, you have this nice family of spherical functions, depending on a holomorphic way on a parameter. In some sense, you're very close here. You also have a holomorphic family of distributions, which you have to normalize a little bit. So they are defined in a little more complicated way. But they can be made holomorphic, and they still satisfy this differential equation, but now in the distribution sense, because they really are distributions at some singular values of S. There might be some distributions supported on a lower dimensional submanifold. Otherwise, it's very similar. At least formally, it looks very similar. Now we also have a discrete part corresponding to the eigenvalues. And here we have the convolution with also spherical distributions. And sometimes these psi k's are the same as the phi's from the family. But here it can happen that the space of spherical distributions for a specific parameter can be of dimension 2. So sometimes it can be that you have this phi s, but you have a second one. And sometimes you take another one. So I don't want to be too explicit here, but it can be written in this way. Just want to say that the description of these spherical distributions is a little more delicate than in the Riemannian case. What is explicit is the C function. It's as explicit as in the Riemannian case. It's a quotient of gamma functions depending on S, and also here the coefficients you have are also very explicit depending on the eigenvalue. So everything is quite explicit. So there's no reason to not expect that you could not do similar things as in the Riemannian case. Maybe a small side remark, which I might take up a little later. This map that maps a function f to its kind of projection onto the generalized eigenspace for the Laplacian, the convolution with the spherical distribution, can, just as in the Riemannian case, be written as the composition of a Fourier transform, which maps to something on the boundary, and a Poisson transform, which maps a function on the boundary to a function on the symmetric space. And here the boundary is something like the isotropic cone, also modulo this U1 action. It can be written as G modulo P for P a parabolic subgroup. So this is again very similar to the Riemannian case. And it's something you need to analyze the residue representations at the end. So maybe just keep this in mind. The point is we have a spectral decomposition and it's rather explicit. So let's try to use it to find some resonances, to do some meromorphic extension. So we have this spectral decomposition, and for CC infinity function it's pointwise. Everything converges nicely, the integral and the infinite sum. We apply the resolvent in the same way as for Riemannian symmetric spaces, or as in the Euclidean case, we just divide by some spectral parameter minus zeta squared, both in the discrete and the continuous part. And at this point, the discrete part does not really cause any problems, because it's just a sum over terms which we know are meromorphic in zeta. I mean, the only dependence in zeta is here. We know this is a holomorphic function in zeta, except at the points zeta k and zeta minus k. And that's where we have poles, and we also could compute the residues. So this is already meromorphic as a function in the whole complex plane. This one is not. It's at the point it's only defined for zeta in the positive in the upper half plane, because then this one avoids 0, or this one avoids real numbers. And again, we would like to shift the contour of integration to a copy of the real line moved into the lower half plane. And well, maybe the spoiler is you can do this, everything works, but you have to overcome some technical difficulties, and that's maybe what I would like to talk about in the next 10-15 minutes. First of all, you have to justify the contour shift. In the Euclidean case, I said we use the Paley-Wiener theorem, and the Paley-Wiener theorem tells you the Fourier transform of a compactly supported smooth function decays exponentially at infinity. So when you do the contour shift, you have boundary terms at infinity, but they will, since the function will exponentially decay at infinity, they will just vanish. There's nothing there. Here, this is not so clear. So we would have to integrate over a finite point of a finite piece of the line, shift this, And then we also have these boundary strips. Why do those integrals vanish when we move to infinity? Second difficulty is we would have to determine the residue here when we do the contour shift. And in the Riemannian symmetric case, this had to do with poles of 1 over the c function. And on the real axis, this does not have any poles in the Riemannian case, but as soon as we shifted, the c function, or 1 over the c function, had poles. And that was exactly what was responsible for the resonances in the Riemannian symmetric case. Here the c function is a little more involved and will have a little more delicate meromorphic behavior. So that's another challenge. And the last challenge is, well, in the Riemannian case, there was no discrete part. So everything that showed up as a residue here when doing the contour shift contributed to a resonance, gave you a resonance. Now it could in principle happen that you have something from a discrete part that gives you a pole here, and you get something from the contour shift from the continuous part that gives you another pole, and then those poles are the same. So you have two terms with the same pole, and there could be cancellation. They could cancel, or you could have to add them and combine them to something. So that's something that's maybe the most technical part of the story. Okay, let me maybe briefly say something about these 3 points. Let me first say something about the contour shift. We would like to shift contour, like to understand how, well, we understand the growth of 1 over this function, but what about the growth or the holomorphicity of this? How does this behave? Especially for large real part, because that's where we have to control the boundary terms. First of all, this c function is a meromorphic function, consists of a quotient of gamma functions, and it's very explicit. So by using classical analysis, classical Stirling's formula, we can just figure out the growth rate as the real part goes to infinity. That's not a challenge. Now this family of spherical distributions that we have here is something we have to control as well, and that's luckily again holomorphic in the parameter. So it's a nice holomorphic function. But how does this behave when the real part of nu goes to infinity? So for this we need a Paley-Wiener theorem for the Fourier transform on this symmetric space. And in the Riemannian case, Hilgert and Pasquale used the Helgerson's Paley-Wiener theorem. That provided exactly the right decay at infinity to justify the contour shift. In the non-Riemannian case, there is a Paley-Wiener theorem for a general semi-simple symmetric space, but it requires that the function f is k-finite, and that's quite a large restriction. We would like to do this for a general test function in CC infinity. So either one has to try to extend this Feynman-Schlicht result to the non-k-finite case. We did this in this specific situation by hand. So here's the small proposition. You can show that the term that you have to control as the real part of your spectral parameter goes to infinity is decaying faster than 1 over any polynomial. So for any n, you have this decay, and the decay is uniform as long as the imaginary part is bounded. So we're only shifting the contour in a bounded region, so that's fine. And it's also uniform in the point on the symmetric space, at least as long as it stays in a compact subset. And this decay is enough, because if you integrate over a strip of fixed length, decay faster than 1 over any polynomial is good enough to have 0 in the limit. So that's exactly what we needed. And it's quite delicate because this will, the C functions will give you something exponential, and this one will also give you something exponential, but it's exactly the same exponential, so they cancel. And that's why you get the polynomial decay. And you should not, maybe that's maybe a comment, you should not really view this as a Paley-Wiener theorem. Paley-Wiener theorem gives you a characterization of the Fourier image. This is only the easy part. You start with something compactly supported and show that the Fourier transform is of decay. We did not show that if the Fourier transform has a certain decay, then it comes from a compactly supported smooth function. That would be the hard part. So this is kind of only the easy direction. But that's the contour shift. Now we're able to shift the contour. But when we shift the contour, we might pick up residues. So what are the poles of the function we're integrating? And again, this part is well understood. We know exactly where this one becomes 0. How about the rest? What are the poles in a fixed region where I do the contour shift, and what are the possible residues? And it's here where things become a little more delicate than in the Riemannian case. So I said that these spherical distributions are holomorphic family, but this holomorphic family could be 0 for some values of nu. You could renormalize if you want, but still it has a little more delicate holomorphic behavior. So for the Riemannian symmetric space, the spherical functions are always non-zero, so that's nothing you have to worry about. But here you do. But luckily, this is known by the work of Frahm. So you can just use the results from Frahm's paper about the spectral decomposition. The remaining part is this denominator with C functions. And I said these are very explicit, so it's an explicit quotient of gamma function, which you can sit down and work out what the poles are. And the difference between, again, the Riemannian and this pseudo-Riemannian case is that in the Riemannian case, you have poles of at most order 1. And here you could also have poles of order 2. So if you multiply something which has, say, a pole of order 2 and something which is 0, you can still have something, you can still have a pole. If order -2 and order 1, they add up to order -1. You could still have a pole of order 1. Or even worse, you have a pole of order 2. So you have a -2 term in the Laurent expansion, and this one is not 0. Then the whole thing has a pole of order 2. But when you do the contour shift in the residue formula, you only pick up the terms of degree -1 in the Laurent expansion. And they are much more difficult to handle. So there are meromorphic technicalities that have to be overcome in this setting. But luckily, everything is explicit for these hyperbolic spaces, so that's possible. Now the last challenge, I said there's possible cancellation between residues and eigenvalues. So if we start with the resolvent formula that we had from before, the spectral decomposition, applied the resolvent, we add these into the denominators, do the contour shift, the discrete part stays the same. Here we shift the contour, and after we have shifted the contour, as in the Euclidean case, this becomes holomorphic in a certain region. So we did extend holomorphically or meromorphically across the real line into part of the lower half plane, and if we choose this n, the contour shift large enough, we get holomorphicity basically in the whole complex plane. But we pick up residues of this expression, and now we have these two sums, one over the eigenvalues and one over the residues. What are the poles on both sides? Here we have to analyze the poles of the C function also. And do we have some cancellation? And that can happen, and crazy things can happen here. Sometimes you have full cancellation, sometimes you have every term here cancels with exactly one term here, completely. So in the case where you have hyperbolic spaces over the reals, and both P and Q are odd, you do start with discrete spectrum here, but everything cancels. So the resolvent will actually be holomorphic in the lower half. There will not be any poles. So no resonances. Sometimes you have to combine them. And this is actually what happens in most cases. This part will give you something, and this part will give you something for the same eigenvalue, and you have to combine them. And it's exactly the right combination that shows that in those two cases, the spherical distribution that you get by adding these two is one that corresponds to a finite dimensional residue representation. So miraculously, they actually fit exactly together. And something you do not see in the Riemannian case either is that the resolvent might actually have poles of order 2. So the meromorphic extension of the resolvent to this full complex plane is possible, but the extension has sometimes poles of order 2. This always happens if P is even and Q is odd in the real case. So I do not want to be too specific here because these things quickly become technical, but this is kind of a flavor of what's happening. Let me try to state the results in a way that's hopefully not too technical. So the first thing is, I think that hopefully became clear through the last few slides, you can always extend the resolvent in a meromorphic way to the whole complex plane. And this corresponds to the result of extending this original resolvent to a double cover of the pointed complex plane. You might pick up resonances. In the upper half plane, it's the eigenvalues. That's not surprising. That's the same as you get for compact manifolds. This is something you do not see in the Riemannian case. On the real line, you sometimes get a resonance at 0. This is kind of the branch point of your covering. And this depends, here or you see that it gets technical. In some cases you do, in most cases you don't. But you do sometimes get a resonance there. And the lower half plane, that's what lives on the second sheet of your double covering. You typically also get resonances. And in most cases, let's say all these cases, and for some real cases as well, they are located in similar positions as in the Riemannian case. You remember it was minus I rho plus an integer, and it's the same here. The problem is that for some other situations, especially the real case where P and Q are even or odd, you have crazy behavior. Sometimes you have no resonances, sometimes you do, sometimes you have double poles and so on. So here it's too tedious to state the precise result, but you can figure it out. But maybe the credo is that in most cases it behaves very much like in the Riemannian case. And now trying to answer the last question of this problem that I formulated at the beginning. For each resonance, you get this residue operator as an operator from CC infinity to distributions. And the image is the representation of your isometry group, and it turns out to be irreducible in every case. And you can determine it explicitly. For these kind of trivial resonances in the upper half plane, you just get the orthogonal projection onto the corresponding eigenspace. And you did not have eigenspaces in the Riemannian symmetric space setting, but here you do. But these are not interesting physically. The interesting ones are the ones lying on the other sheet. That's in the lower half plane. For the possible resonance at 0, you get something you could call a limit of discrete series, which you can also describe explicitly. And in this last case, again, let me skip these special cases, but in most cases, where the resonances are located in the same spot as in the Riemannian case, the images of these residue operators are again finite dimensional, and you can give the highest weight and determine these representations explicitly. So the final result is, apart from some technical special cases, very similar to the Riemannian situation, but you need much more technical tools in the proof. Okay, that's what I want to say. Thanks for listening.
Thank you very much for a very interesting talk. Are there some questions?
So the thing is, you said that it is really related to something study of large time behavior of this Schrodinger probability. In what way it is related to this? The first slide, you said that it is related to study of this large time behavior of long-term behavior of the corresponding Schrodinger equation.
Yeah, I'm not fully sure, but if you, for example, consider this trivial case of a compact Riemannian manifold, then the eigenvalues are related to the long-term behavior. Because if delta is acting by an eigenvalue, then in the long term the solutions will behave like e to the it times the eigenvalue. So it's some kind of phase that you get. I think it's something similar for non-compact resonances, but I'm not sure. I'm not an expert in this, so yeah, I don't think I can say anything profound on this in the non.
So actually, I somehow failed to really understand this, the motivation of this problem. Okay, I understand this is a really good problem. But the thing is, suppose you are really, suppose you are able to find all the resonance of this some symmetric spaces or something. So how does it will help in analysis? That is, really, I don't understand that. So is
No,
what is the
I don't
motivation
know.
of studying this? What is the motivation of studying this problem? Okay, this problem is fine. Do you have any?
No, I'm afraid I don't know enough. Yeah, PDE theory or mathematical physics here to say something in this direction.
Might be. Okay, anyway.
I think they are interested in scattering theory. These problems arise naturally in scattering theory.
I think in mathematical physics there's a different notion of a priori a different notion of resonances. That's scattering resonances, and they are defined as something using scattering operators. And in many situations, those things are the same, but they are defined in different ways. So yeah, I think these resonances also have something to say in scattering theory. But again, I cannot say something profound in this direction.
Okay, yeah.
From representation theory, one motivation is to exhibit some interesting representations, and they are the images of these residue operators that show up somehow associated to the space.
Yes. Okay.
Are there some more questions? Yeah, looks like there are no more questions. So we would like to thank you once again for an interesting